In this video, I'm going to talk about set equality, complement, and difference. Equality we've already been using. We've been assuming that we know what set equality is because we do. I've been doing things like saying, okay, let's have A be equal to 1, 2, 3, 4. I've been saying things like, well, order doesn't matter, so the set 1, 2, 3, 4 is 4, 3, 2, 1. They're equal. But I want to just make sure we have this formalized. So two sets are equal if they contain the same elements. We don't care how those elements are written. We don't care how the set is expressed. As long as the two sets have the same elements, they are equal. Like B equals the set of all x such that 1 is less than or equal to x is less than or equal to 4, and x is a natural number. Then A is equal to B. We can say that these sets are equal. One other thing to say about equality, and this is going to feel like a weird thing to say when I first introduce it, but when you have to do proofs using sets, you are going to be amazed how incredibly useful this actually is. So another way to define the equality of sets is two sets E and F are equal if E is contained in F and F is contained in E. So if every element from E is also in F and every element from F is also in E, then obviously they have to be the same sets, they have to have the same elements. The reason why I say this is important, and I will not do an example right now, but I will just give you an idea of why the heck I even bother to write this, is that if you are doing a proof and you are trying to prove that two sets are equal, sometimes these sets will be written in really convoluted ways or described in really convoluted ways where you're like, oh, E is the set arising from blah, 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 in the case of blah, 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 with these conditions. Something, much less straightforward than the sets we've encountered so far. If you run into a situation like that and you want to show that E and F are equal, sometimes it's easier to say, okay, let's take the set E and prove something easier by just proving that E is contained in F. And then let's take the set F and just prove that it's contained in E. And sometimes doing those proofs can be way easier than trying to establish from the get-go that both have the exact same elements in them. So this is why we bother with this definition, and this is why I say it's an important definition. Next up, set complement. The complement of a set does require us to have some context and understand what the universe is. We don't have to understand the actual physical universe, but when we're talking about sets, we usually are assuming that we're working within some sort of context. Before we talk about complement, we need to know what context are we in, / what is the universe or the universal set. In most of the examples I've done so far when describing sets, I have only worked with integers. So far, my universe has been the set of integers. We will look back at this in a second and we will define the complement. The complement of a set A, written A with a line over it, or A bar, is all of the elements that are not in A. For example, let us have A equal the set of all x such that x is an even integer. Then, if we wanted to determine what A complement is, we want everything that's not an even integer, so the things that are not even integers are odd integers. So A complement is the set of all x such that x is an odd integer. And this is where this universe comes into play, because I'm not writing that A complement contains all odd integers, my cat data, and my Nalgene bottle. Because we're not working in a context where my cat or my Nalgene bottle are relevant. We're working in a context where we're talking about integers. We're talking about A being the set of even integers. We need to make sure that our complement is specific to the context that we're working in. So in this case, we're assuming that the universe U is the integers. Someone else might present a set of integers, but realistically the universe that they're working in is a set of all real numbers. So then if you're looking for the complement, you need to know that your complement is in the context of all real numbers, not just in the context of integers, because obviously the complement will be different. If U were to be the set of all real numbers, then using the same A as above, A complement is now going to look quite different. A complement is going to be the set of all x in R such that x is not an even integer. So it's going to be the set of all real numbers, removing any even integers. We end up with a much different set here when our universe changes to be the real numbers versus the set here when our universe is the integers. Last, we have set difference. This is written in a couple ways. So two sets A and B, the difference of them, can be written in one of two ways. It can be expressed as A minus B or A slash B, like this. Both of them mean the same exact thing. Different people use different notation. And it is the set of all elements that are in A with all elements from B removed. So it's the set of all elements that are in A but not in B. For example, let's look at Z, which is the set of all integers, minus n is going to be Z, but we remove all of the numbers from the natural numbers. We're just left with the negative integers. And also 0, because 0 is not included in the natural numbers, so it survives the subtraction Z minus n. We can also do something like this. Maybe we have 1 through 10 minus the set 5 through 15. When we do a subtraction like this, we're going to take the first set, take away everything that's in the second set, and we are left with 1, 2, 3, and 4. And you will notice that the set has some elements, such as 15, that are not in the first set, and you just ignore those. We just ask ourselves what elements from that set also are in our second set, and then we remove those. Okay, I am going to stop there.
Hey, I can't get back into vinyl. Yeah, you wouldn't. You're not serious enough. Well, what? I like music. You probably dig that band that played in Swingers, that 90s film. I like Dookie Buttons.